Hello and welcome back to Calculus 3, section 14.2 on line integrals. So, what are we doing on line integral? Well, what is the line integral? Before we answer that, what is one of the most, known applications of integration? Area under the curve. Very good. So, we know from Calc 1 that if you have a function f of x from a to b and that defines the area, if the function is above x-axis, integral a to b of f of x dx is going to calculate the area of the shaded region. Now, this is a 2D integration, and I will remind you that this particular shape is flat. It's flat. The x-axis is straight and flat, and then above it is another flat, right? So that's this, right? It's flat. What happens if I am to curve the function? So it's still going to have the top to be whatever the wavy function is, but I want the sides, the shaded region, the red region, to look like a curtain that it's hanging off the wall, right? So how do you find the area of that curtain? And moreover, you can't flatten that curtain because it's made out of glass. It's made out of glass, so you can't straighten it. Right? If it was metal, you just hang it out right with a hammer. But it's made out of glass. So the first time you hit it with a hammer, it's going to break. So now we have Calc 3 line integrals. I have a 3D space of x, y, z. I have some kind of a line. This line we are going to call a C, right? And on top of this line, you just have a curtain, okay? You have a curtain that has some kind of a top on top, and that is your f of xy. And now you want the area of the curtain. Now, C is parametricized. C is parametricized, meaning that it's given as x is some function of t and y is some function of t. So we are going to find the area of the curtain now. And for this we are going to do all of those good old rectangles and so on and so on. There is a definition for this, but again, this is one of those cases where you have the definition, but you're not using definition to do calculations. So, definition of the line integral. With the arc length as a parameter, now we know that we changed the arc length parameter into dt, right? The t parameter is, let's say, time or whatever, so that we can actually do the easier calculation. So suppose the scalar valued function f is defined on the smooth curve meaning it's differentiable. Smooth curve is parametricized by the arc length, so we have r of s is a vector x of s and y of s. So the line integral of f over c is, and now we have integral c f that is parametricized by s, so x and y, there we go, ds is equal to the limit. Now this is going to be the same stuff that you use in Calculus 1. So delta goes to 0 and k goes from 1 to n, and we have the f of x of the sk and y sk times delta sk. Now again, this is just a definition for us to understand. I tried well enough, but you can see the rectangles up there. So what I did is I took the curtain that it's all wavy and I shredded it into long pieces, right? And then calculated area of each one of those rectangles and then added all of those rectangles together. So if you are parametricizing on the arc length, which is the waviness of that C line, when we cut certain pieces, right, you just get the long strips of that curtain, and then we just calculate each one independently and add them all up. Now we send the number of those strips to infinity, make delta S infinitely small, which makes the whole calculation to be exact. Now that's not the way to calculate this thing. We want to figure out a better way to calculate. So we are going to define the line integral through the theorem 14.1, which is actually the way to compute. So to compute line integrals, use below. Process below. So what do we have? We have that the integral over the curve C of f ds, which is what we had before, is now going to be given as the integral a to b, there's your good old a to b, f, which is parametricized now with the x of t and y of t. So now you need to know your parametrizations, times the absolute r prime dt. Now we can also write this as f of x t y of t times the square root of x prime squared plus y prime squared. Right, those are all of t. Maybe I should add that. dt. So this is the formula that we are going to use to compute line integrals. Now clearly you have to know parametrization, otherwise you are doomed. Doomed, yes. So let's take a look at an example of evaluating line integral. They say average temperature of on a circle Well, that's worked out.
Average temperature on a circle.
You don't know the temperature of a circle?
Not the average.
Yeah,
Temperature of a circle. Wow, that'd be there.
You never touched a hot circle? See what I did there?
Yeah.
See what I did there?
So it's a disk. But that's done in a book. So let me scroll through these 15,000 pages.
From those pizza pans when you take them out of the oven? Circle. Huh? Wow. For the pizza, yeah. That's a hot circle. You're just cutting up a circle into triangles.
What a cool.
All right, ready?
Let's send you to that.
Problem number 16. You are supposed to calculate the integral x squared plus y squared ds, where C is the line segment from 0, 0 to 5, 5. So line segment from 0, 0 to 5, 5. Do what?
Do you take a lot of lighting?
You will have to use the other paper, yes. Now, the first order of business is for us to figure out what C is. So parameterization. We need to know how to parametricize lines and parabolas and circles and all of these kind of things, because all of these calculations now will require of us to have that parameterization so we can use it to figure out the rest. So parameterization. I'll write everything out. Straight line was parametricized by x of t was equal to x0 plus at. Y of t was y0 plus bt, and z of t was z0 plus ct. If you are in a 2D realm, we don't need, right? So this is for the 2D, only x and y, and all three are for 3D. So now, what do I have? I have a line segment that goes from 0, 0 to 5, 5. Line segment that goes from 0, 0 to 5, 5. I can actually, well, we know the way to figure this out. We find the vector v, which is going to be vector of 5 minus 0 and 5 minus 0, which is vector 5, 5. And now we use that vector and our initial point to create the line. So our R is going to be the given by the x1, so that's going to be 0 plus 5t, comma 0 plus 5t. So I used the first two equations over here. And we have our parameterization R, which is 5t, 5t. Once I have this, the rest is easy, because this over here is your x of t, and this over here is your y of t. So now all you need to do is to sub everything in. The integral you are supposed to solve is x squared plus y squared ds. Now what we are going to do is integral. Oh, I forgot to say that in order to go from 0, 0 to 5, 5, your t must be between 0 and 5. Sorry, 0 and 1. So plug in t equals 0, the vector will become a location. So if you plug in time equals 0 in here, it will be 0, 0, and that will be the first location. If you plug in time t equals 1 second or 1 hour, then this will be 5, 5, and that's the terminal location. So vector gives you the direction and the magnitude, but we now care only about initial and final destination. So I need this, guys, I need this. You have to have this. For a circle, it's going to be 0 to 2 pi, or half a circle, 0 to pi. You need this because these are your limits on the integral. See, immediately as I put the integral down, I remembered, oh, I didn't do the t part. Because your a and b on that integral, the integral is dt at the end. Those are the limits that you have to find for parameterization. If you have issues with parameterization, if you haven't had parameterization earlier, I know I did talk about it 2 or 3 times in the class, chapter 10 in this book, and then go to study plan for the homework and work some exercises out. You need to know how to parametrize. So now, what do I have? I have x squared. Well, x is 5t, so that's 5t squared plus another 5t squared. This is 0 and 1 on limits. And now I need r prime, magnitude of r prime. Well, I know that the r prime is given as 5, 5 when you take the derivatives. So magnitude of that one is going to be what? It's going to be square root of 25 plus 25, yes. So let's put 5 squared plus 5 squared. Guys, sometimes this is going to be a function. So, and you have dt at the end. Yes.
Wait, what is that?
Liz. So now we compute this monstrosity and problem 16 is solved. So 0 to 1, open parenthesis, I have 25t squared plus 25t squared, that's 50t squared, times 5 root 5. So let's go one step at a time. So 50t squared times 5 root 2 and dt. So 50 times this is 250 root 2. Kick that in front of the integral. Integral 0 to 1 of t squared dt. So we are going to integrate now and get t cubed over 3 from 0 to 1 to give me 250 root 2 over 3. Yay! There it is. Problem number 18 is moving alongside the parabola. That's cool. So what do you have? You have a curtain that it's bent in the shape of the parabola. If you are to pick up the circle, you will see the parabola this way, and that is your C. So this line over here is C. But that stands on a desk like this. And then the function that it's inside of the integral is the one that makes whatever wavy top we have. So now we have to do parameterization to fit all of these kind of things and calculate the area. So we are looking for the integral over the line C of xy to the 1/3 ds. They should have just said the cube root. I'm going to do that. Someone is on the math train over there. That's all I can hear. So C is given with y is equal to x squared for x values between 0 and 1. Oh, be ready for all kinds of exotic cases over there. What happened?
Why?
Yes. Well, we'll get there. So, parametrization. The easiest way to parametrize something is to use the dummy variable t for x and be done. So in this case, if I just say y equals t squared and x equals t, you can see that by plugging in t from the second equation into the first one, you get y equals x squared. And we also have that x goes from 0 to 1, but because x and t are the same in this parametrization, I have that t is also going from 0 to 1, yes, because I need those for the limits. I said that's one of the ways to do parametrization.
Where did it 0 to 1?
In the problem.
Oh, it's T.
T is x, very good.
Ooh, I like that symbol.
Points.
What was it?
So now I'm going to, so I have my parametrization, so I can write the integral 0 to 1, and then I have my cube root of, and instead of x I have to write t, and instead of y I have to write t squared. So you see that that cube root is going to be very handy there to kill the cube on t's, right? And then we have the square root of the partial of the derivative of x, which is 1 squared, plus derivative of y is 2t squared, and then we have dt. I'm just going to make sure that one more time you guys understand, know, or whatever, that this thingy over here is r prime, magnitude of r prime. Also, if you didn't know, when you have parametric equations, you should know this, but when you have parametric equations, your r of t, right, is given by t squared. So once you have parametric equations, if you're in 3D, you'll have 3 equations. If you're in 7D, you'll have 7 equations. Once you have the parametrization, that parametrization is creating your good old R that you know all the way from chapter 11, 12, whatever the hell we did this. That R is the R over here that you get to. Now you can remember this as the function, the vector valued function that gave you position, and then its derivative is the velocity, but the absolute value of the velocity is speed. So you can remember this formula easily by remembering, once you parametrize everything, whatever ends up to be the first place of where the cube root is, and then times the speed, because that's going to be the derivatives, right? And then the absolute value of it. So now we compute this thing. Integral 0 to 1, cube root of t cubed, right, the square root of 1 plus 4t squared dt. So now the cube root and the cube die, and we do u sub. Very good. Basic u sub, it's 1 plus 4t squared du is 8t dt. I don't have 8, so I'll plug 8 in and 1/8 in front, right, to make sure it works. So now 1/8 integral, 0 limit is on the bottom, it becomes 1. 1 limit on top becomes 5 when I plug those into the u sub. So plug in 0 on the bottom limit into u sub, we have 1 plus 0 is 1. Plug the 1 then the 1 squared is 1, 4 times 1 is 4, plus 1 is 5. So limits are changed, and all I need to do now is just to have u to 1/2 du, and that's easy thing to solve. That's going to be u to the 3/2 divided by the 3/2 from 1 to 5, and we have this cancels, so 1/12 u to the 3/2 computed from 1 to 5. So we have 1/12, plug in 5, we have 5 to the 3/2 over, no, it's just 5 to the 3/2. You use the u sub equation. You plug each one. Как one? Minus 1 raised to the 3/2. And that's equal to some number over here.
Blah. Is that your answer? Blah. Well, no, I'm asking you like that because I don't know.
That is an answer. You'll figure out decimals.
So if I write blah,
It's going to be wrong.
well, no, well, somebody else knows.
Do what I say, know what I do.
Do what? No, but monkey see, monkey do. That's how things have always been. I see you do what I have to do myself.
You just said do.
No, he said you do what I think, not what I say. That's awesome.
No, I said
Oh,
do what I say, not what I do.
oh, that's right.
3D version of the same is just going to be integral over region C of a function ds is going to be good old integral a to b, and now we parametricize everything. So f of x of t, y of t, z of t, r prime of t dt, which can also be, right, so I'll just write, instead of copying everything again, I'll just put this square root of x prime squared plus y prime squared plus z prime squared. That goes there. So now that you know all of these rules and stuff, it's time for you to enjoy a problem. On your own, no hand holding.
I don't know if I can do that well.
Alright, so let's see what can we master. Oh, maybe I can just put something. Yeah, let's do something. Alright, so integrate x plus y plus z ds. No, that's not it. I'm thinking now, nah. So C is circle R, which is given by 2 cosine theta, 0, 2 sine theta. And theta or t, whatever, it's the same thing. So let's put these. There we go. Have fun.
Is there a number for this? Or you just make it up?
I was trying to make something up, but then I decided not to, so this 25. I wanted to put in the helix, but I can save that for the test.
Oh, this is not bad.
No, it's not. Of course.
Just. No, it's over 30.
Yeah.
Loud car goals. That sure looks pretty good on you, man.
That was.
Been working out.
What?
What? I like the color though. It's a good color. It's like a navy blue with the mustard yellow. Classic duo.
I got negative.
What kind of car was it?
Yeah.
Was the one that wastes gas, obviously. Like, just to pull out a parking lot, $20 right there. Yeah, gone. It's a truck.
It was a truck.
Yeah. There you go, another $20 right there.
No, it's just a bad exhaust. It doesn't mean he's wasting gas. I mean, it does. It helps a little bit.
You have a truck to drive to Harvey and go back. It's not that you are moving.
Cut off.
Just keep it at home. Did you get 7?
No.
Okay, good, because 7 is wrong.
One of these days you're gonna say that, and 7 will be the answer.
The odds are so not in the favor of that being true because
Yeah, but like,
Why you want to bet how
It's
funny
you.
you right now? That's
mine is a negative.
That's a challenge.
Wait. Oh yeah, because you're minus 1.5 is positive 1.
I didn't say it's impossible, Jake. I said the odds are. Well, please do find one so I can.
If this goes in at 0, positive 1.
Yeah. All right. So does it have to be calculus 3 or can it be anything?
Oh shit.
So it's 0.
So
Do you want calculus 3? 7 in the calculus section or 7 out?
I don't care.
We'll count There's chapter 11.
All right. So in this problem, guys, parameterization is already given to you. So that makes this problem easier because you don't have to worry about anything. Now, when you have a parameterization given, you just plow through calculations. So we can immediately find R prime, and in this case, R prime is going to be negative 2 sine t 0 to cosine t, and then find the magnitude as the square root of negative 2 sine t squared plus 0 squared plus 2 cosine t squared. And this works out to be 2. Very good. Works out to be 2. Because you will factor out 2, you will get sine squared plus cosine squared. That's 1. So, right, you will factor out 4. Square root of 4 is 2. Good. So now, there we go. So now we have our integral is 0 to 2 pi. Now it's parametricized with t that it's actually theta. So we could have used theta instead. Your x is given as 2 cosine t plus y0 plus z is 2 sine t. So those are given in a parametrization times 2 and then dt. So we can kick out 4. I guess this problem is too easy, so let's find something.
Wait, it's not minus?
What happened?
Yeah.
He didn't do the integral yet. That was so sad.
It was.
That was upsetting.
What happened?
I was just like, isn't it? Never mind.
What's upsetting? Oh, it involves feelings? Keep me out of it. So, we have 4 sine of 2 pi minus cosine of 2 pi. You guys having way too much fun.
Well, we got the answer though.
Oh, you did get the answer?
It's gonna be so long. Yeah.
8.
Wow.
Wait, it's negative.
No.
Yeah, I got
I didn't plug in the actual, like.
Yeah, because you get negative 4 for the
Why did you
cosine,
say
and then
sine
you have
theta
it
instead of
minus
sine
1, so you
0?
get-
So, this is 0.
Yeah.
And this is 0. Oh, this is not supposed to say theta. It's supposed to say 0.
Why don't you subtract the last cosine?
Yeah, that's
Because
supposed to be-
minus
it's
a
supposed to
minus.
It's a minus and a minus in a fundamental theorem of calculus.
It's minus minus.
Yeah.
It's minus.
So it's negative.
Plus cosine.
Oh.
It's negative 1.
Wait, hold on.
It's negative 1 plus 1.
Uh,
Yeah.
That's what 25 possible. 0.
4. And then negative 1 plus. Oh, yes, it's 0. Good.
I had
All right. All right, let's open the gates of hell.
That's the answer. It's saying it's not that bad.
The line integrals.
Gotta deliver on that promise.
No, actually not.
Now let's see who's going to see this one. So line integrals of a vector field. Yes, the line integrals of the vector field. So we are going to now have a vector field involved where we can calculate, remember that, integrals do calculate the area under the curve, but they also are known as, for other applications, where you can actually calculate the accumulation of stuff. So you can calculate the total energy or the total amount of rainfall or so. So it's not just application to find area under the curve. We can also say, all right, here is the formula that the function that has the rainfall, right? And then you integrate the rainfall, and let's say t is measured in months. So you integrate between, I don't know, 2 and 5, and you get how much rain fell in a particular area from February through May, right? So you can figure these things out as you are going along. So now we are not calculating the area of the face of the curtain. We are calculating the accumulation of stuff that passes through it. How much light does it get through the window? Right? There's a radial vector field that is in a center where? For the light coming through the window, that's a radial field coming up from where?
The sun.
The sun. Right? So the light rays, the radiation of the sun is going to be, right? Yeah, it bent a little bit and also, but it's for the purposes of understanding this, it's just fine.
Okay. So it's like light would get beamed directly on.
So now, let's go with the definition, and again we are going to have the theorem of how to compute it. So, we have, title first. So we have the line integral of a vector field. Live integral. Definition. Let F be a vector field that is continuous on the region containing a smooth oriented curve C parametricized by arc length let T be the unit tangent vector yes. Who remembers the formula for unit vector T? R prime divided by the magnitude of R prime.
Okay. What was the question? What's the? That's the tangent vector. It was the.
So let T be the unit tangent vector at each point of C. Consistent with the orientation. The line integral of F over C is integral F dot T ds. Again, this is the definition on which we are getting to understand what is happening. And without me drawing what's already there in the book, I'm going to show you the graphic over there. You see that ellipse on top? That's going to be your smooth parametricized curve. You know that you can parametricize ellipse also with a cosine and a sine that have different numbers, right? So if the numbers are the same, it's a circle. If the numbers are different, it's an ellipse. Now, if you're looking at this, right, you have your tangent vectors here, right, and that this curve is the curve C. The dot product of those two, right, in the integral parametricized on the this will calculate the amount of stuff passing through the invisible curtain that is here. And again, the vector field is the one that is all over the place. Remember that the vector field, you assign the point in space, and then you draw the vectors out of that. Or just see, here's the vector field right there. Done. There we go. So you can feel it. You can feel it. Now this makes too much noise, so we'll just keep the fan off. What happened? As I thought. So now, to compute. What do you mean job? What is that?
Are you writing stuff? What? Okay.
So to compute this, the line integral for vector field. So to compute the line integral of vector field, use below. So what do we have? We have that integral of a to b of f dotted with r prime of t dt can be computed as, and now we just do the dot product, because you have the three components of f, which is three components of the vector field. You have f, g, h, and then you have three components of the r vector, right? And then you those are x, y, and z, and those are all primed. So now you just work out the dot product between them to get the f from the vector field times x prime plus g from the vector field times y prime plus h from the vector field times z prime and dt. Now, there is a short way of writing this, and you will see this in your homework and then exam and stuff like that. So, short way notation is integral c, and then we just put f dx plus g dy plus h dz, and this is the notation that we actually haven't used before, but right, so that's that, and then that is also equal to the integral c of f dr. So that's also a way, that's a vector notation. You see that both, because it's a dot product, right? Because your dr has dx, dy, dz, and your vector f has f, g, and h in it. Yes?
So from the definition, where did the magnitude, like, so the vector t is like the unit vector, right?
Unit vector, yes.
So where is the magnitude that's on the bottom?
That's the one that transforms your ds into dt. Yes, so there's a transformation that we learned a long time ago in chapter 11.9. Is the first time when we did the transformation with that, or maybe even earlier. It's somewhere in chapter 11 we did that transformation. So yes, that's the actual magnitude goes with the transformation there. So yeah, that's it. So we have this, and the two-dimensional component of this obviously would just have no h and z. The rest of the stuff is so everything else is the same. Now, the three experts over there should explain all of this to the rest of the class. Let's see. Go on. What's happening now? What did we just do?
Yeah, I think he's asking again.
Yeah, 3, yes. Okay, line integral of the vector function, great.
Dot product.
It's a dot product of, yeah, it's on the screen, yeah, I know. What was the definition before? He was talking some tangent vector. What was that about? What is this calculating? How does it work? See, when you miss those kind of things, and the stream is unfortunately not going to show me bending that piece of paper. I have to figure out how to include that as well. But
Get a video cam.
Well, no, just link it to a YouTube video and just say this is this.
We'll put a tripod right in the middle of the room.
Yeah.
And
I gotta try that.
well, it's too late now.
Watch.
Now, the next part of this is one word that you, or well, actually there are two words here. I just need to, oh, there they are. So, look at that. And look at that. And then this. So, a lot of grades die right there. Because you know that when you are parametricizing a circle, you can go and parametricize at r cosine t, r sine t, or r sine t, r cosine t. The only difference there is the way you would move along that circle. These calculations are very sensitive to that. Yes?
That's what you're trying to do, helix. That's an example.
Yes, I wanted to do the helix, but that's, yeah, we'll do. So it's very important which way the things wind, right? Because as a helix, and that's a very good example, Ryan, as a helix, it can spiral out counterclockwise or clockwise, right? And in that case, you guys, I mean, it looks the same, but you know it's not the same because it spirals the opposite way. So you have to make sure that these, that if you are, if you have a circle involved in things that have, well, all of them have orientation. Parabola has orientation as well. They all go in the side of the increasing t. So as you are parametricizing, right, remember that we had y equals x squared to parametricize, and we said, okay, x equals to t, and then y equals to t squared. Now this over here is the parametric set. We also said that our x was, but let's make it now more interesting. Let's just make that t is in between 0 and 3. So when t is equal to 0, your first point is 0, 0. When t is equal to 1, your next point is 1, 1. When t is equal to 2, it's 2, 4. And finally, when t equals to 3, it's 3, 9. What is the only part of the graph that you have? Nothing else exists other than starts at 0, 0 and shoots up and ends at 3, 9. That's that. With everything else in between. Right? So 1, 1 and 2, 4. So you have your 0, 0. You have your 1, 1. You have your 2, 4. Oh, I have one extra. Alright, so kill this one over here. No! Ah, got it. So, observe, and I'll put it in blood. There you go. That is the orientation. It goes from 0, 0 into 3, 9. Now, why and how is that important? Well, remember that vectors have orientation, right? So the minus sign makes it go the other way. And if you have the wrong way, you have the wrong direction, then obviously your answer is going to be off. You're going to get 7 and then it's going to be wrong, right? The book does talk about different paths on page something, 1067. On page 1067, they tell you the quarter circle from 0, 1 to 1, 0, and then a quarter circle as a negative C1 is from 1, 0 to 0, 1. So they flip that. So when you are going around the quarter circle, these are all different paths to get from point A to point B. Let's see, this is point P, this is point Q. Look what you can do. You can have the red path over here, and the red path is from Q to P. That would be counterclockwise. So if you're using red, your parameterization R is going to be R cosine T, R sine T, and this R is whatever the radius is. Maybe I should we use rho?
No.
I don't want you confusing it with this R.
Okay.
No Greek. Now, we can also have the blue path, which goes from P to Q. So the red path was, I'll put Q to P. Now we're going to have R parameterization to be R sine T, R cosine T, and that's P to Q. And now look at the green path. The green path is this path. Ooh. So the green path now is actually having the two line segments, and it's also going from T to Q. Guys, these are all different. Good effort. So when you are dealing with these things, and again, this is also going to be important later in our section 14.4 in the Green's theorem. Parametrization, right, of the green lines now. So this green line over here is parametricized as x equals 0, y equals negative t, and for these two, t is going from 0 to 1. So let's test this. Well, I should say 0 to r, since I am using r as a radius, or I can just put a number in front of it. So we know that this is the radius is r. So this point over here is 0 r, and this point over here is r 0. So let's try it. When t is equal to 0, then you are at 0, 0. See, I have this backwards, right? When t is equal to 0, I have 0, 0, and that's bad. I need to be at 0, r. So this is r minus t, right? Yes, r minus t.
Why?
Yes, y is r minus t. Yes.
Oh my God.
So, yes. So now this is your parametric set. Now test it. Well, I put what I thought was right, and then when I checked it, it was wrong. So then I fixed it. Now let's check again. If I plug in 0 for t, right, because the first value t takes on as time ticks on is going to be 0. When I plug in 0 for t, that dies, and I have 0r, and 0r is my starting point p, because I'm going down the line, right? I want to go p to q. So now, okay, that's great. And now endpoint is when t is equal to r. When t is equal to r, I get r minus r. R minus r is equal to 0, so I get 0, 0, and yay, right? We're home. The second parametrization here is when x is equal to t, and y is equal to 0, and t is between 0 and r. So now let's check. I really don't like using r, because I don't want you guys confusing it with this r. So when t is equal to 0, I'm at 0, 0. My motion begins at 0, 0, because I just came from walking down the y-axis into the origin. So now I should start at the origin to walk towards q. So my parametrization here is 0, and then R. So R0, good. So now the green creates another path for you to get from P to Q, which is clearly different. So the two words over here, the oriented curve, and then being inconsistent with orientation means that you have to make sure that that you are using the correct parameterization, because one more time you will be plugging in these. This is your x and this is your y, and you will be plugging those into equations within your. You have your x prime and y prime, and you know that when you have them switched because you use the wrong orientation, your minus signs are going to be in wrong spots, or your sines and cosines are going to be in wrong spots. So that will create wrong answers. So be very careful about that. Ryan, you wanted to ask something.
So how would a wording be on a question where we'd have to figure out what pathway to use?
Well, generally, the questions are very clear on which path you are using. It will say moving along the semicircle clockwise. Okay. Bam, that's the standard. That's the standard parameterization that you are talking about since Calc 2. Or they say quarter circle counterclockwise, right? No, counterclockwise is the standard, cosine then sine, and then clockwise is backwards, sine and cosine. So those are the ones. So these are the things you have to be careful with. So now the problems over here, right? You want to find the. So let's go and find. We're halfway through this lecture, by the way. This is. We still have so much to do. So when we come back tomorrow, we'll have to finish this and then push further. So let's take a look at all right, so here's problem. So when we're done with problem 36, we'll call it quits, and then we'll pick up tomorrow. So problem 36. Your vector field is given as negative y and then x. And then you are on parabola y equal x squared from 0, 0 to 1, 1. So you are computing the line integral. Now you know that your line integral c is f dot t ds, but we are not using that form because that form is only for our theory. We are using the form, this form. So most of the time, maybe I should lightly box this over here. So you will be using this thing over here to actually compute things because that one has everything in it. And if you are on a 2D, like we are now on 2D, you will just ignore the a to z part at the end. So we will be using now integral a to b, and that's fx prime plus gy prime dt, right? Now you know your f is in terms of x and y and your g's, but we'll get there. So first I need to parametricize this. So here we go in green, like all of this stuff over here is going to say, oh, parabola, let's use the easy one. X equals t, y equals t squared. And then t is trapped between 0 and 1, and you test it. When t is equal to 0, both x and y are 0. When t is equal to 1, both x and y are 1. So we moved from 1, 1 to 1, 0. Now, the problem could have been switched with these points, like that. So what then?
Would you switch the negative from
One. Just one.
It will be 1 minus t and 1 minus t squared. You see, there's your parameterization. This is where your hours are going to go into. Figuring out these kind of things. You have to sit down and play with those equations. You can't just reverse and put that t is smaller, that 1 is smaller than t is smaller than 0. That makes no sense. That 1 is actually eventually smaller than 0. Right? And no, you can't use negative 1. so you have to figure these things out. And that's where the hours of learning Calculus 3 go. So now that I have this parameterization here creates vector r, which is t squared, which actually gives me r prime, which is 1 and 2t. Now, I'm going to use blue color to mark this thing, because by the end of putting all of this into the formula, you'll probably stay cross-eyed. Look at this. Your vector field, capital F, is your F and your G. And your R is your X and your Y. And your R prime is your X prime and your Y prime. There we go. So now, guys, this will be a multiple layer of substitution to plug all of this in. So focus. 0 to 1, that's given here. All right? So the limits 0 and 1 are given in your t. You have to figure that out from parameterization. Now the tough part. F. You see, F is given as negative. Let me go this way. F is given as negative y, and y is given as t squared. Stare at that. That is the string that you have to follow, because your integral ultimately is dt. I can't see any f's, any x's, any y's. Everything has to be in terms of t. So I'll do this one more time. This is the formula. This is where we start. So I need to plug in f first. Great. What's f? Well, f is negative y. Wait, what's y? Oh yeah, y is t squared. So what do I put? I put negative t squared. There we go. So this is where you pause the video, right? And you stare at this for 15 minutes. So f is the negative y, but y is t squared. So when I plug in t squared up there, so technically, what is this f over here? This f over here, right? I can also write this f as negative t squared and t, right? This is negative t squared t. But anyway, now I need x prime. X prime is hiding here, guys. That's where the x prime is. So x prime is just 1 times 1. Plus g. Great. Where's g? Where's g? G is here, g is x, and x is t. Nice. So that's just t times, and now I need y prime. Y prime is here. So that's 2t. And then we have dt. Yay, we're done. Now it's algebra. Well, calculus. Negative t squared plus 2t squared dt is going to be integral of t squared dt, which is t cubed over 3 from 0 to 1, which is 1/3. And there it is, 1/3. Not 7, right?
So if you did the first way to integrate or whatever, would you have to make separate parameterized equations still? You know what I mean? So you would have to find your x prime and y prime. Like
we used this, but as you can see, each one of these f's is eventually a t somehow.
Could you just
So this is where you go home, you make coffee, you sit down, and then you snake your way through this to find what plugs where. We will finish this lecture tomorrow. There will be 14.2 line integrals part 2 because we're halfway through. See you tomorrow.